This structure, built some 12,000 years ago, that's 6,000 years before Stonehenge, 5,000 years before the first pyramid, highlights that for millennia, humans have used the engineering method to solve problems. This is Göbekli Tepe, an ancient ruin in southern Turkey. Stone structures cover 9 hectaacres, about 18 football fields. Filled with circular rooms, its purpose remains a mystery. Archaeologists detect no signs of habitation, no kitchens, cooking fires, large-scale storage of food, or traces of agriculture. Embedded in the stone walls of the rooms are T-shaped pillars. Many rooms feature 2 T-pillars in the center. None of these pillars serve a structural purpose, but instead are decorative. Carved into the pillars are lions, bears, wild boars, lizards, spiders, and surprisingly, ducks. Not only are the stones beautifully carved, they are placed with precision. To see the degree of precision, look at the circular room I showed you initially. At the center are the remains of 2 T-pillars. The tops fell off long ago. They are 18 feet tall and weigh at least 8 tons. If we look at this room from above, keep your eye on the 2 central pillars highlighted in red, you see 2 circular rooms nearby, which each have the same arrangement of pillars at their center. The pillars in the 2 rooms at the bottom sit on a line with little deviation. On this line, the pillars have been set so that their long sides are perpendicular to the line. And if we locate the exact centers between the pillars and the 2 lower circles, and connect them to the center of the pillars in the circle above, we inscribe an equilateral triangle. Its sides deviate less than 1.5% from perfection. This is unlikely to be coincidental, nor the result of some self-organization. My point is that these stones are erected in a purposefully designed layout, not haphazard, that responds to societal needs, which means that Göbekli Tepe is an engineered object. Its construction shows the hallmarks of engineering, the development and repeated use of specialized techniques for construction, to quarry the large limestone slabs, to transport them, often kilometers, cut and polish them, and carve designs. So the people of Göbekli Tepe created all this by applying the engineering method. The method we still use today to build skyscrapers, scan images, or design microchips. We follow, as do all engineering creators, the same steps. But this powerful method, the engineering method, is an all but hidden process that few of us have heard of, let alone understand, even though it influences every aspect of our lives. In this video series, I explore the essence of that engineering method. The age of Göbekli Tepe highlights that the engineering method long predates science, which conflicts with the commonplace notion that engineering somehow arises from the scientific method. By that I mean a notion of scientific discovery and understanding followed by an application. So I start my investigation of the engineering method by asking, do engineers need science? And here's the answer. This is a model of Sainte-Chapelle, a stunning 13th century building. Sainte-Chapelle was designed and constructed by a team who had never learned basic arithmetic or the geometry taught today in 3rd grade, let alone anything we'd call science. In fact, they had no standardized length because a foot varied from region to region. The medieval engineers aspired to create a building that celebrated a spiritual world by streaming light through the structure's walls. And perhaps no other cathedral was this light as stunning as in Sainte-Chapelle. Sunlight was transformed by the stained glass windows into a diffuse red, blue, and gold that glimmers on the chapel sculptures and gilded arches. To create these stunning displays of light, to house these giant stained glass windows, the masons built vast walls by constructing spectacularly high ceilings. How did these engineers, called masons, know how to carve a cathedral's thousands of building blocks to create, when assembled, not only beauty, but also stability? How did they create such enduring beauty without today's knowledge of strength of materials and material properties and elastic theory? Like all great engineers, they drew on past knowledge. They used an architectural element that originated in present-day Pakistan. Notice that Saint-Tropez has, as do all cathedrals, pointed arches, some 6 on the front, at least 10 on each side, and on the back 6 more. And, of course, many pointed arches support the ceiling of Saint-Tropez. This arch was first seen in the 2nd century AD in Buddhist architecture. This is Taktai Bhati, a Buddhist monastery located in what is now Pakistan. It rests on the crest of a high hill and so survived for centuries. The pointed arch is used throughout the structure, its shape most clearly highlighted in this entrance to a tunnel. From there it spread east where, by the 7th century, it appeared often in Islamic architecture. They chose this pointed arch over the arch used in the Romans' extraordinary Pantheon. This building, typical of all imperial Roman architecture, features a semicircular arch. It is exactly half of a circle. This arch was rejected by medieval engineers because its width grows too fast with its height. To see the problem, consider a semicircular arch that is 10 meters in width. It is, of course, 5 meters in height. Now, if I double the span covered, from 10 meters to 20 meters, you see that the height is now 10 meters. It is doubled. Contrast this to the pointed arch. As the arch increases in height, the span covered stays the same. So if chapels and cathedrals with high ceilings used the Roman semicircular arch, they would gobble up entire city blocks, and the cost of the necessary stone would skyrocket. The difference between using a pointed versus a semicircular arch startles when comparing Saint-Tropez and the Pantheon. Note how Saint-Tropez is nearly the same height as the Pantheon, yet just a little over a third as wide. That's a huge reduction in stone. Although medieval engineers didn't adopt this Roman semicircular arch, from the Romans they inherited the key idea that enabled them to build their stunning cathedrals that have stood for centuries. This model of one of the many pointed arches in Saint-Tropez highlights what medieval engineers learned from the Romans. To safely and economically construct this arch, the medieval engineers had to correctly size the thickness of this wall, which supports the arch. If this wall were too thin, the weight of the arch would buckle the wall, the structure would collapse. If too thick, stone would be wasted at a huge cost, and the desired open space inside the cathedral diminished. To size the wall, the medieval builder used a rule inherited from the Romans, a rule that created the Pantheon. The rule, called the proportional rule, is simple. A stable structure results when the supporting wall's thickness is about 1/4 or 1/5 of the arch's span. If an arch's span were this long, then you divide it into about 4 equal parts and use one of these parts to size the wall's thickness. If you increase the span covered, then you proportionally increase the wall's width. The key idea of the Romans was this. The stability of a building was in its shape. That is, the correct geometry of a building guarantees a stable structure. And that's a sharp contrast today where we have a structural theory used to calculate the stresses, to assess the strength of a material, and so on. The medieval engineers had no such thing, so they used this proportional rule. But there's a problem with this. The masons knew no mathematics. They likely had never learned to read, let alone calculate a dimensional ratio. Nor, as I've said, did they even have a yardstick. So this rule was not a calculation, not an exercise in pencil and paper Euclidean geometry, or even a basic mathematical proportion, but instead an action. Let me show you on this section of Saint-Tropez. Again, our goal is to find the proper thickness of this wall. The mason would have a life-size chalk drawing of the interior of this arch on the floor of the drawing room. Instead, I've drawn the arch on a large sheet of paper, which I'll use to show you in miniature how the mason sized the supporting wall of an arch. In addition to this arch drawing or template, you need a piece of string. The mason would have used a rope. I need to drape it over the arch, so I'll insert map pins along the arch to support the string. The mason would have done this on the floor, so he would simply lay the rope on top of his drawing. Now, drape the rope over the arch, mark the string at the base of the arch, then cut the string so it is only as long as the arch. Next, lay the string on the ground and fold it into thirds. I've marked the thirds with pink tape here. The mason would have used colored chalk. Of course, today we'd just use a ruler, but remember, the mason had no ruler, nor did he know any math. With the rope now marked into 3 sections of equal length, return it to its original place along the arch template. We see that this divides the arch into 3 equal sections. Let's mark one of them. Then pin one end of a new string to that marked spot. Draw a taut and pin it to the base of the arch. We need to attach to the base a length of string exactly equal to the distance from the spot a third of the way along the arch, so I just folded the rope and marked it. And then draw that taut and in line with the pin section, then pin it to the base. The distance from that pin to the inner line is the width of the wall. And let's compare it to the arch section from Saint-Tropez. If I superimpose it on the string construction, you can see that it matches. This rule for sizing arch supports ensured centuries of stability, all without even the simplest mathematical calculation. With that rule, we've arrived at the core of the engineering method. The proportional rule doesn't come from some scientific analysis of stone and its properties. It comes from centuries of experience, from trial and error. It's called a rule of thumb, more formally, a heuristic, an imprecise method used as a shortcut to find the solution to a problem, often by narrowing the range of possible solutions. Here, a mason sized a wall's width in a matter of minutes without understanding the fundamental material properties of stone and without understanding the mathematics needed to apply the rule. That's a paradigm for the engineering method, solving problems using rules of thumb that cause the best change in a poorly understood situation using available resources. That's a sharp contrast with the scientific method, because these rules of thumb are only guides that offer a high probability of success, but no guarantee. And unlike a scientific theory, a rule of thumb is never in a sense disproved. That hundreds of cathedrals are still around today, standing for 800 or 900 years, is proof of that. Instead of being disproved, this rule of thumb for stone became outdated, not wrong, as iron and steel replaced stone. To use geometry alone to ensure stability of a building would be folly. Today, engineers use sophisticated theories of strength and stiffness to ensure stability, to develop more appropriate rules of thumb to create structures with steel I-beams. Yet, no doubt, there's a question in your mind. I've talked about buildings constructed 8 or so centuries ago. So surely you might wonder, is engineering based on rules of thumb antiquated? Are these rules mere placeholders until the real, precise answers arrived in our scientific age? But that line of thought misunderstands the purpose of the engineering method, which is to solve practical problems before we have full scientific knowledge. In the next video, I'll explore how engineers work their way around that lack of scientific understanding, how they overcome uncertainty. I'm Bill Hammack, the Engineer Guy.